right? So this is the thickness now. Thickness is perpendicular to the shear flow. Okay, so the Q at B is equal to Q at C plus, so the width now is, so 40 plus 10 is 50. The depth is 20. The Y bar is 60 minus by 20 divided by 2. Okay, so Q at C is 7500 plus by 60 minus 10, so 50 times by 50 times by 20 is equal to 50,000. Let me do it again. 60 minus by 10, Y bar is, yep, times by 20 times by 50. Okay, so this is equal to plus or 7500, 575. Let me do it again. 750 plus 50, 1, 2, 3. Yep. Okay, so this is millimeter cube, or 57520 times 10 to the power minus 9 meter cube. Okay, so the shear stress at point B is equal to V over I, constant. So this is equal to 57500 times 10 to the power minus 9. And then we divide by the thickness of 20 times 10 to the power minus 3. Okay, so 57500 power minus 9 divided by 20 power minus 3 is your 2.875 times 10 to the power minus 3 V over I. Okay, so the last one is we're going to find at point C, just stress at point C. And this is where we trigger in non-thin wall analysis. Right, now the thickness is equal to 60 millimeters. Okay, now the thickness is equal to 60. So the first moment of area of C, so the area that we are going to consider now is this whole area now when it's at point C. Everything in yellow. Okay, everything. Okay, so we know that we have to have twice of QB. Okay, plus, so now the width is 60. The depth is also coincide to be 60. Multiplied by 60 divided by 2. Okay, so the twice of QB is 57500 plus the width is 60, the depth is 60 times by 60 by 2 is 10800, 3 zeros. So this is equal to 2 times 57500 plus a 108123 is equal to 223 millimeter cube, or 223 times 10 to the power minus 9 meter cube. Let me calculate again. Plus by 2 times the 57500. 223. Yep. Okay. So now we find at point C, right? V over I. So this is equal to 223123 times 10 to the power minus 9. Thickness now is 60 times 10 to the power minus 2. Minus 3, sorry. So this will be equal to 223123 power minus 9 divided by 60 power minus 3. It's 3.716. And something very interesting happened now, right? Or 3.717, right? Now, right, this is at point C is at its tau max. Hey, is it point C? No, point A. I do apologize. Okay. Shear stress at point A. So now our shear stress at point A is the biggest, right? Before that, the previous example, when the forces are, the shear force is vertical, the maximum is at point B, but now horizontally, the maximum is at what? Point A, right? Okay, so So from here, we can now determine the V over I ratio. So shear stress at point A is equal to our tau max, which is equal to our our 75 times 10 to the power 6. Okay, so this will be equal to 3.717 times 10 to the power minus 3 V over I. So we know that V over I is equal to 75 power 6 divided by 3.717 power minus 3 is equal to 20.17178 times 10 to the power 9, and this is in Newton per meter to the power 4. Okay, so from here, the shear stress at point B will be equal to 20.178 times 10 to the power 9, and at point B is 2.875 times 10 to the power minus 3. Okay, so 20.178 power 9 times 2.875 power minus 3 is equal to 58.012 times 10 to the power 6 Pascal. Okay, let me do it again. 20.178 power 9 times 2.875 power minus 3, 50. Yep. And then we can find the shear stress at point C is equal to 20.178 times 10 to the power 9 multiply. So at point A, the coefficient is 750 times 10 to the power minus 6. So 20.178 power 9 times 750 power minus 6 is equal to 15.13, 15.134 times 10 to the power 6 Pascal. Okay. So you can see if the force is running vertically or horizontally, right? The position of the maximum shearing stress can change. Okay, and don't always assume it to be at the what? Don't always assume it to be at the centroid. Okay, as I said in our example, it is all dependent on the tau max will occur either at Q max or at where? At T mid. Okay, either one. They are competing with one another. Okay, so it's the ratio that we have to watch for. Okay, I would like to do another example. Okay, regarding thin wall, because thin wall can really be confusing, and I like to handle confusing problems with you all. So I want to look at example. Yeah, no, this example is too easy. I'm going to delete. I'm going to bring this one over here. I want to look at this example over here. Okay, let me cut this away. Bring this here. Okay, I want to look at this example with you guys. Okay, and why the first how to acquire the first moment of area is very important. Okay, example number 3. The shear force V is acting on our structure. Determine the shear flow at point A and the shear flow at point B. Okay, so we have to find the shear flow at point A and the shear flow at point B. And I'm going to sketch this out. Okay, I'm going to sketch this out. And this is the solution. Okay, this is the solution. Whatever. Okay, we will see is, or we will try to make sense of their solution later on. Okay, So in a problem like, okay, in a problem like this, when I post the solution, I don't want you all to like look at the solution. Okay, I think I have to explain how this solution manual has to be used. Okay, so for this problem, I'm not going to find I. Okay, I'm going to take I directly. Okay, how to find QA and QB? I'm not going to look at their numbers now. Okay, I just want to look at their figures. Okay, don't look at their numbers. Their numbers, it's their numbers. Okay, we do ourselves. What is important is this number over here. At the end of the day, these are the key numbers that we have to be the same. Okay, how they get there? Why is it this number? You have to figure out. Don't like, it's like that. Okay, we are going to figure this out. Okay, right. So I'm going to sketch this structure out. Okay, so we have 125 and 1010. Okay, so 125 and 40. So this is, wait, 2, 4, 6, 7. Okay. And then at a certain 30 position away, we have another section, right? Okay. And then we have 30, 10. Then we have another 100, and then goes all the way down, and it's 10. Okay. So 2, 4, 6, 8. I only need to draw half over here. Okay. This is directly at point A. Right, that's the point A. And then at point B, capital A. Capital A. And over here is a capital B. So we are going to design the shear flow, and over here, this is our centroid. Okay. So we still apply the same rule. Okay, we design the shear flow first. The web control the flow. Right? So over here, you have your Vy. Right? That's your Vy. And then your Q will do this. Right? So you realize that this is one of the terminal. And then this one, you can draw towards the center also. Right? You want to draw inwards or you want to draw outwards, you decide. But they also meet at one point. Right? So this is another what? Terminal. Okay. So point A is easy. Right? Point A is easy to find first moment of area. But what is the first moment of point B? Okay. So what area to take? And I think I did write this down before earlier. Hold on, now I forget where I've written it. The area of consideration is relative from the terminal. From the terminal. I'll put this here. Okay. it's always the first moment of area will give us the most problem. Okay. So we are going to apply what we have written down here from the terminal. So at point A, okay, the Q at point A, or the shear, the question wants us to find the shear flow for point A, and we know that it is a thin wall box beam. Okay, and we are going to have 2Q. Okay, right. So from here, we know that the Q at point A is equal. So the width is what? So we look at over here. The width is 125. The depth is 10. The Y bar is 10, 100.